Hey everyone, we're Team 12 and today we're presenting improving small code models with self-generated instruction data. We know from scaling laws that larger models usually perform better on difficult tasks like code generation. But scaling has real costs. Training needs multiple high end GPUs, inference is slow and memory heavy, and instruction tuning relies on large annotated datasets. That makes big models hard to use outside well resourced environments. Our goal here is to explore how far we can push smaller models by using smarter training methods instead of more parameters and therefore reduce the overall resource use. In our work, we re-implement the self-code aligned pipeline. The core idea is that just as humans, the model can improve learning from its own self-generated tasks and responses. Starting from the stack dataset, we run the full pipeline and obtain about 40K instruction response pairs. We run a three-stage pipeline. The first step in the existing pipeline is to filter functions from the stack dataset to retain quality functions at each filtering stage, which is type checking, decontamination, quality filtering, and deduplication. This helps us retain quality seed functions. From step one, we get about 250K seed functions and use the base model itself to generate diverse programming instructions. We do this by learning the key concepts from each seed function, concepts such as recursion, dynamic programming, and graph traversal. And then we tell the model to generate a problem based on these concepts using few shot learning. The output instruction set has well specified programming tasks. We then use our generated instruction set to generate multiple possible solutions for the given instruction. For each instruction, we make the model generate multiple responses along with their own test cases and run the code in the sandbox environment, and then label the passing code solution as either accepted and the failing code solution as rejected. The instruction and accepted response pairs are then used for supervised fine tuning. We use pass at k to evaluate our correctness. K is the number of solutions generated for a problem. And even if one of them successfully runs in the sandbox, it's a success and is averaged out over the number of instructions. Because we were able to put together a pre existing preference dataset, triplets of instruction, correct response, and incorrect response, we decided to try out an offline alignment method like DPO to improve our model reasoning. The core idea of DPO is simple. Instead of learning a reward model, the DPO directly adjusts the model's logics so that it assigns higher likelihood to the preferred response and lower likelihood to the rejected response, relative to a frozen reference model. In our case, it's the SFT model. This reference model introduces an implicit KL divergence constraint, which prevents the updated model from drifting too far while still aligning it with the preference data. The model showed superior performance when evaluated on human eval and MBPP, indicating that the model performs well even in low resource environment. One unexpected result is that the base model StarCoder 23B has a MBPP score of 0. This is because the model is used for generating assert statements rather than entire code, due to which probably the score is 0. After applying DPO, we observed a small improvement on human eval, likely because it's small to medium complexity tasks that align well with DPO's tendency to reinforce preferred solution patterns. In contrast, MBPP showed little change as it's a broader task diversity limits the impact of narrow preference tuning. And the base model already performs strongly on the MBPP style problems. Self-code align shows that small and medium-sized LLMs can achieve large model-level code generation performance when aligned with high-quality, self-generated, execution-validated data. For future scope, we want to explore PEFT and alternative RL-style objectives to improve generalization across more diverse coding tasks. Thank you.